Okay. All right. So let me do just a brief introduction. So hello, everyone. So definitely welcome you to our webinar on variational analysis and optimization. And today is actually our first talk in this year. And we are very happy to have Nam Ho-Nguyen from the business school at the Sydney University to join us to give a talk. Just a bit of background, I think Nam received his bachelor from ANU in 2013. And then he went on to do a PhD at Carnegie Mellon in USA. After completing his PhD in 2019, then he spent 1 year at Wisconsin University and worked with Stephen Wright. And we are very happy that he comes back last year, at the second half of the last year, I think, to come back to Australia again. And just want to mention that he received several awards, including the most recent one is the Gerard Thompson Doctoral Dissertation Award in Management Science in 2019. So I think without further ado, I'm going to hand over to Nam. So the floor is yours now.
Right. Thanks, Goyin, and thanks to all the organizers for inviting me to give this seminar. Very happy to be able to present my work in this series. I just want to confirm that everyone can see the slides okay, and you can hear me okay?
Yeah, everything is good.
Okay, cool. Okay, so the talk is called Coordinate Descent Without Coordinates, Tangent Subspace Descent on Riemannian Manifolds. I should mention that this is joint work with David Huckleberry-Gutman, who's actually on the call today. He prefers to be called Huck. He's at Texas Tech University in the Industrial Manufacturing and Systems Engineering department there. And yeah, we met at Carnegie Mellon actually, when we were both PhD students at Carnegie Mellon. So this is joint work with him. Okay, so by way of introduction, I want to mention or introduce this problem of nonlinear optimization, where we want to minimize some function f, right? So choose some variables x to minimize f, and we're choosing our variables x from some subset C of Rn, right? And typically we assume they're both convex, but I'm sure we all know that, you know, studying these problems when non-convexity is present is becoming more and more common. I'm not going to talk about any particular application today, but I do want to mention that this problem has a lot of applications in various areas, and I've just listed, you know, 3 areas here: economics, finance, engineering, and statistics and machine learning here. And in particular, the last one, statistics and machine learning, has been, I think, driving a lot of the research in nonlinear optimization in recent times. So this is the flavor of the problem we're going to study. In particular, we're going to think about numerical methods for nonlinear optimization. And I should say I'm not a historian, so maybe I got some of these years wrong, but just from anecdotal evidence that I've seen from papers, I think there are 3 eras for how numerical methods in nonlinear optimization has developed. So the first one is this early era where first order methods were studied, such as gradient descent, Frank-Wolf, and so on. Right? So that was pre-1980s. And then the second era is from 1980s to 2000s, in particular the 1990s, where interior point methods and other second order methods were developed. So these methods were more sophisticated than first order methods. They involved more elaborate algorithms and also had slightly higher complexity. But that meant that, you know, they were very accurate. And there was a lot of work put in to develop, you know, the theory, but also software packages, industry-ready software packages, so that they can be used on generic problems in a lot of applications. But, you know, I guess this last maybe 2 decades or so, this large-scale era, we've seen a lot more data. And so that means that we encounter so-called large-scale problems, where the number of variables is very large, or the number of constraints may be very large. But that means that, you know, these elaborate algorithms, you know, interior point methods involving, you know, sophisticated operations like matrix inversion may not work so well for these large-scale problems. So people change, you know, compromised a little and said, maybe we're willing to put up with less accuracy, but, you know, we want to be able to do cheap iterations. So that means that people are focused again on first-order methods in an attempt to solve these large-scale problems. So the talk will focus on first-order methods of a certain form. I want to mention that for this nonlinear optimization problem over Rn, the most basic first-order method is gradient descent. So it's an iterative method, and if we are at a certain iteration and we've generated the point xk, the method is very simple. What we do to get an improving point is that we move in the direction of the negative gradient of the function f from xk. All right, so that's gradient descent, and this is, you know, the standard, the most common first-order, most well-known first-order method. And then there are variants of that, such as proximal gradient and stochastic gradient descent. So I'm not going to talk about proximal gradient or stochastic gradient descent today, but the one I want to focus on is coordinate descent. Right? So coordinate descent is a variant of gradient descent when you have very large problems with very large number of variables m. Right? And what you do in those what you can do in those situations is, instead of updating or computing the full gradient, you compute a partial derivative in one coordinate, say coordinate j, right? And then you just update that one coordinate. So you do a similar descent step, but it's only in that one coordinate, right? And then what you can do is cycle over all of those coordinates, and that finishes one outer iteration to get xk plus 1, right? An alternative to cycling is you can just randomly pick a coordinate, and that gets you to randomized coordinate descent. So this is the method that we're going to look at. In particular, this talk is going to focus on how to generalize this method to problems where our domain is not Rn, but instead it's a manifold. Right? So just to be more precise, this is the problem we're going to consider. We're still going to optimize a function f, but now our domain is a manifold. And I guess here, I should say that, you know, if you're familiar with differential geometry and the formal definitions of these concepts, you may find this talk a little frustrating, because I'm not going to, you know, try and formally define all the concepts from differential geometry. I want to kind of give the bare minimum that we as optimizers need to understand how certain algorithms from the Euclidean setting will translate to the manifold setting. So it's like, I do want to say that up front, but I do apologize up front for that, if you do have that background. But just for people who don't have the background in differential geometry, when I say a manifold, informally, I'm thinking of some set, right, where if you look at the whole set, you may see some curvature, right? But if you look at a point and a small neighborhood around that point, then it looks flat, right? So the canonical example is the sphere or Earth, right? If you look at all of Earth, then you can see it's a curved shape. But if you look at, you know, if you're at any one point on Earth and, you know, you're very small, then the ground essentially looks flat, right? More formally, a smooth manifold is just some topological space where every point X on the manifold has some neighborhood that is homeomorphic to some open set of Rn, right? And this essentially captures the idea of locally flat. We also want to say that these different homeomorphisms for different neighborhoods are compatible in some precise sense that I'm not going to define in this talk because it's a technical condition. But essentially, this means that we can do calculus across the manifold. Okay, so this is the optimization problem that we're interested in. We want to optimize F over a manifold domain. Just to give you another visualization of a manifold, this curve set here is the manifold, and the point that we're considering is right here. I don't know if you can see my mouse, but it's in the middle of this patch here, right? And so if we look at the neighborhood around that point, we can map it to some Euclidean space. So that's what I mean by the manifold being locally flat. You can think of sets similar as to this, and things like the sphere or the torus and so on. Okay. So the question is that you may have now is, what is the benefit of, even modeling? What is the benefit of thinking about optimization problems with a manifold domain? Right? Do we gain any modeling power? And I have two answers to that. The first one is that some domains have some structural symmetry or invariance, and manifolds are kind of designed to capture this kind of structure, in particular geometric structure, right? And the second one is that some problems, if you just think of them in the traditional Euclidean space, they may be non-convex, but when you model them with through a manifold and you endow the manifold with something called a Riemannian metric, which I'll come back to later, it makes the problem geodesically convex. So this concept of geodesic convexity actually generalizes convexity, and so it allows you to solve certain problems efficiently. So that's why people have been looking at optimization problems with a manifold domain. Okay, so I want to illustrate this with three examples. The first one is the problem of principal component analysis. So this is a very common problem in data analysis. The idea is that we have some points U1 to UK in Rn, and these may be points that we get from data, right? And what we want to do is project these points to some p-dimensional subspace of Rn, right? Reasons for this may be to be able to store them more efficiently or run certain statistical or machine learning algorithms more effectively, and so on. So, but this is a key problem in data analysis, right? So now we want to project these onto a p-dimensional subspace, and we can write the projection of a point UK as x transpose times UK, where X is a matrix, an n by p matrix, right, with orthonormal columns, right? So X transpose X is equal to the identity, right? And so this is the projection of UK onto the subspace spanned by the columns of X, right? And then this sum here with the Euclidean, the squared Euclidean norm is simply an expression for the variance of these projected points, right? So the problem is, because we want to preserve as much of the variance as possible, that means we're trying to maximize the variance, or choose the X, or choose the projection that maximizes this variance expression here. So this is principal component analysis, right? And obviously you may know that this has been studied. You know, you don't have to study this as an optimization problem with a manifold domain. But the advantage is that, you know, manifold optimization algorithms can implicitly handle these orthonormal constraints, right? By exploiting the structure of the manifold, which this is the manifold here. It's just the set of all matrices that satisfy these orthonormal constraints. And this is called the Stiefel manifold. So we can exploit that structure if we think of the problem as having a manifold domain. Okay. The second example is low rank matrix approximation. So again, this is, you know, has been studied a lot in recent years, and the typical way that the problem is framed is that we have n customers and k products, right? And each customer has some rating of the product. So we have n times k pairs of rating. Well, yeah, you have n times k different ratings, and these ratings can be arranged into an n by k matrix U, right? But of course, in practice, we don't see every single rating. We only see a few pairs, right? So we can see the pairs omega here, which is a subset of all the possible pairs. And so we want to predict what the ratings on the pairs that we don't see are, right? And the way we do that is we're going to try and estimate this matrix X, which is our estimate all the ratings, right? An n by k matrix. But we're going to impose so-called low rank structure on X. So X, we want to factorize it as C transpose P, where C and P are m by n and m by k, respectively. And that means this manifold is the manifold of all n by k matrices with rank at most m, right? So we're going to find a low rank matrix that approximates the ratings on the pairs that we do see well. So this is that low rank matrix approximation problem. And the hypothesis for the low rank is that each customer has an attribute vector Ci, and the product J has an attribute vector Pj. And the hypothesis is that the true rating Uij from this matrix U, which we don't observe, is just equal to the product, the inner product of Ci and Pj. Right? And the last example I want to talk about is that this so-called Gaussian Fisher-Rao distance, right? So the Fisher-Rao distance is, you know, a more general concept that we think that has been used in, you know, information geometry and statistics, and it's a metric on parametric families of probability distributions, right? So if we specialize that to the parametric family of zero mean Gaussians, right, of a certain, you know, dimension, then the parameters are essentially positive definite matrices. This variance matrix is the covariance matrix is what we need to know, right, to parameterize this family, right? And so if you go through the maths and compute what this Fisher-Rao distance is between two zero mean Gaussians with different covariance matrices, this is the expression that we get, right? And it turns out that this, if for example, if you fix sigma 0, the first covariance matrix, and allow sigma 1 to vary, as a function of sigma 1, this thing is non-convex in the traditional Euclidean geometry. But if you endow the positive definite matrices, I mean, if you think of that as a manifold and you endow it with something called its intrinsic metric, then it actually becomes geodesically convex in the intrinsic metrics, and this fact has been exploited in certain statistical estimation problems in recent times. Okay, so those are 3 examples. I hope I've convinced you that optimization on manifolds is actually important. Now I want to talk about how do we think about first order methods on manifolds. And as I said before, I'm not going to give precise details on these concepts on manifolds. It's actually, I think it would take a lot longer than 1 hour, but I want to kind of relate certain concepts that we're used to thinking about when we think about first order methods in Rn, in Euclidean space, to their corresponding operation or concept on a general manifold. Right, so the first one is if we have a certain point x on our manifold, we can ask, okay, in which direction can we move from x, right? So if this is our point x here, right, we can ask which direction can we move from x. So as you can see, this picture draws a tangent plane at the point x to the surface M here. So M is, the manifold is the surface. Then the tangent space is this is just the tangent plane, and the tangent plane just tells you which directions you can move. For instance, the tangent plane does not include the direction that just goes straight up from x, right? That would take it completely off the manifold, so we say that's not a valid direction that we can move on the manifold, right? But of course in Rn, right, from any point x, we can just move in any other direction. So in Rn, we think of the tangent space as being simply Rn. Right? Another thing to point out here is that if we change the point x, instead of considering this point x, maybe we consider a point over here, then the tangent space would actually change. So the tangent plane would be different. It would be tilted maybe this way a little. So if your manifold is Rn, and we're thinking in the traditional setting, all these tangent spaces at different points x can be identified, right? But on a manifold, that's not the case. You have to think of Txm and Tym as different kind of vector spaces, even though they are isomorphic to Rn, but you have to think of them as different vector spaces. And so that's the first concept of directions from x in M. The directions are given by a certain tangent space, Txm, and this tangent space can be different for different, points, can be different for different points, I should say. The second one is what is a gradient of f? So we can think of a gradient as being a direction of steepest ascent for a function, and that would imply that the gradient of f for a general manifold is actually a member of the tangent space. All right, so that's one thing we have to keep in mind. The third concept is the Riemannian metric, right? And this object is used to capture geometry on the manifold, right? So formally what it is that for each tangent space, Txm, you want to define an inner product for that tangent space, right? And of course in Rn, because all the tangent spaces are the same, right, you can actually identify them exactly. You can just say that the Riemannian metric is the usual inner product on Rn. But on a general manifold, these the tangent spaces, you have to think of them as different objects. So we have different inner products. But the thing is that as you vary x smoothly, and I'm glossing over this part, how you vary x smoothly, this Riemannian metric will also change smoothly, right? The fourth concept is the concept of parallel transport, and this is really to compare two different tangent vectors in two different tangent spaces. So we have x and y, then we have two different tangent spaces, tx and ty, right? On Rn, right, we can just compare them directly because all the tangent spaces are identical, right? But on a general manifold, there has to be some sort of way to compare it, and the way we do that is through this parallel transport operator that maps tangent vectors in txm to tym, right? The fifth one is probably the most important one, is if we have some vector, some direction vector v in the tangent space at x, how do we actually move on the manifold in that direction v, right? And in Rn, of course, direction vectors can be identified with, you know, points on the manifold itself, so Rn. So when we have a point x and we want to move in the direction v, we just add the vectors, right? But on a manifold, like for instance here, it doesn't really make sense to add x and v because it can take you off the manifold, right? So we have this special operator called the exponential map that allows you to, that gives you a way to move in the direction v. So if this is x and this is v, then the exponential map would map x, would move x from here to maybe somewhere here along this line here, and this line is called actually the geodesic. So it is in a precise sense the length minimizing curve. All right. The final thing I want to mention is the distance. So we can define a metric on a manifold through this Riemannian metric here and this exponential map. So if we have 2 points, x and y is obtained from x by moving in the direction v, then the distance between x and y is just the norm of v. But the norm is taken in terms of the Riemannian metric, right? So remember, v belongs to the tangent space at x. And so when you take the norm, you have to use the inner product from the Riemannian metric for the particular tx, right? And of course, in Rn, you know, we're using the usual inner product, so the distance just becomes the norm of v, the Euclidean norm of v. Okay, so these are, you know, kind of the, I would say the bare minimum that you need to know to kind of understand where these first order methods on manifolds come from, right? Oh, and one other thing I should mention is that when I say that a function is geodesically convex, that means that if you look at this function of t here, which is a function of one variable in R, so t is in a real number, right? And you look at this function mapping t to f of the exponential map applied to t times v, then this function, as a function of R, is convex for any x in the manifold and direction vector v from the tangent space, right? So that's what I mean by geodesically convex. Okay, so this is kind of the background that I wanted to build before I start talking about algorithms on manifolds. Oh, I have an example here for positive definite matrices. So if the manifold is the set of positive definite matrices, the tangent space at each point x on the manifold, so at each positive definite matrix, can be identified with the symmetric matrices, right? And the Riemannian metric at each point x, you can, well, it's given by this expression, and then the parallel transport. So if we have 2 points, x and y, and we have a direction vector v from the tangent space at x, then if you want to parallel transport v into the tangent space of y, this is how you do it. All right? And the exponential map is given by this expression here. And with this expression for the exponential map, the example here, this would turn this function in, well, I should say this, the expression of the exponential map that I mentioned before makes this function geodesically convex according to this definition here. Right, so that's an example just to illustrate these concepts. But now I want to talk about algorithms on manifolds. So I'm just going to look at, the simple algorithm, Riemannian gradient descent. Right? Recall that for gradient descent on a Euclidean space, when you have a point xk, you want to move in the direction of the negative gradient, or some multiple of it, tk. Right? So you want to move in that direction, so you just subtract the gradient from xk. Right? On a manifold, you want to do the same thing. All right? So from xk, you want to move in the direction of the negative gradient. But recall from the previous slide, the way we move is with this exponential map here. So that's why this is what you have to do to generalize gradient descent to the Riemannian setting. We just use the exponential map instead of just subtracting the vectors. Right. So this is the basic algorithm, and we can analyze it in much the same way as in the Euclidean setting. We have to take care in certain parts, but a lot of these concepts translate according to this table here. Okay, but now the problem I want to think about is how do we extend coordinate descent to the manifold setting. So it's not clear what a coordinate is on a manifold. Right? That doesn't necessarily exist. Before I do that, I want to introduce this extension of coordinate descent, subspace descent. So instead of picking a coordinate to descend on, to update, we pick a subspace, right? Sj at iteration j, and then we project the gradient onto that subspace, right? And then we subtract it from the current iterate, right? So that's subspace descent, and we can analyze that in the Euclidean setting, right? And so through subspace descent, it gives us a way to generalize how we think about coordinates on a manifold, right? So instead of coordinates, we're going to relate the concept of coordinates to subspaces of the tangent space, right? And then we're going to construct this algorithm, or write down this algorithm called tangent subspace descent. That's very similar to subspace descent. So we're at the current point xk. And then we cycle at xk. We have 10 m inner iterations to get to xk plus 1. And for each of those inner iterations, j, you pick some subspace of the tangent space that we're currently at, right? Of the tangent space of the point we're currently at. So you have to pick some subspace here, right? And then you do the same thing as what we did on the previous slide, but translating to the language of manifolds, we have to use this exponential map. So here, this is the current point, yk, j minus 1. Then we take the gradient, we project it onto this subspace that we picked, and then we move in the negative direction of that projected gradient, right? And then once we go through all m of those, then we just set xk plus 1 to be ykm, right? And so there are two crucial differences with subspace descent in the Euclidean setting. The first is that in Rn, all the subspaces remain the same, right? So we can just, this part of picking the subspace actually comes before we enter the loop. But on a general manifold, these subspaces, of course, belong to different vector spaces, different tangent spaces, right? So we have to, so on a general manifold, we have to pick these subspaces inside the inner loop, right? So the question is, how do we pick the subspaces, right? And so the first, result that I want to mention is that we do actually need to pay attention to this. This is one of the challenges of generalizing coordinate descent to the manifold setting. That if we choose these subspaces poorly, then we may not converge. And the theorem is that there exists some subspace selection rule which satisfies certain spanning condition that we need to have. But even if it satisfies that spanning condition, we can still find an example where we will see it does not converge. Right, and this is the example here. I'm not going to go through it, but I'm happy to talk about it after if you're curious. But this theorem highlights the need to pay attention to the subspace selection rule, right? So before I get into what the rule we want is, I want to highlight some kind of standard tools in the analysis of these first order methods, right? So if you study, gradient descent on smooth functions and so on, you see a certain result that pops up that relates to consecutive iterates, xk and xk plus 1. And the result says that, if to get to the next xk plus 1, if the function decreases by at least some multiple of the gradient squared, right, then you will have convergence, right? So that's usually what you see. This lemma here kind of augments that a little bit to say that between iterates, either you have this sufficient decrease as a multiple of the norm squared of the gradient, or it just decreases by some fixed amount, eta prime, right? If you have those two conditions, then you will have convergence, right? So kind of the goal of subspace selection is to choose the subspaces and analyze things in such a way that these two conditions are satisfied, right? And so just kind of almost immediately, right, just from the statement of the algorithm, we can show that the sufficient decrease, we can show that the iterates will decrease the function by at least this amount here, right, which is the sum of the gradient projections for the inner iterates y, right? And now we need to relate this term to one of these two conditions here. All right, so that's kind of the challenge of subspace selection. Okay, so now I'm going to introduce the assumption that we make in order to achieve this. And this is the technical definition, right? But the intuitive definition is that when the inner iterates are close, so the inner iterates being, yk1 to ykm, the iterates that we generate in this inner loop here, so the ykj's, when those inner iterates are close, then the subspaces that we choose, so these guys here, SKJs, are close to orthogonal, right? So that's what it means intuitively. More precisely, what it means is that there exists some R and gamma, right? Such that we choose the subspaces so that at the outer iterate K, right, there exists some orthogonal decomposition of the tangent space at the point xk, right? And this orthogonal decomposition and the subspaces have to be related in this way, right? If we look at the distance or the maximum distance between xk and the iterate the inner iterates ykj, if that maximum distance is less than r, then when we compare the orthogonal decomposition to the subspaces that we actually choose, then they have to be close. And the sense that they're close is the following, right? First of all, we have to, we're looking at the operator norm for these, the difference of these two projection operations, right? We have a parallel transport operation here because these subspaces belong to the tangent space at yk j minus 1, right? And we want to compare it to a subspace of the tangent space at xk. So we have to add a parallel transport term here, right? And so we compare this operator here, so the projection operator composed with the parallel transport. We compare this with the projection operator of the subspace from the orthogonal decomposition. And when we compare these two in the induced operator norm from the Riemannian metric, they have to be less than or equal to gamma. So this is the condition that we propose. Okay. And so I'll skip ahead and I'll come back to this slide, but you know, obviously I think you can kind of anticipate that the results will say that when the assumption holds, then we can show that you will have the sufficient decrease conditions holding, right? And that of course implies that when the assumption holds, when you choose the subspaces to satisfy that assumption, then you will have convergence. So here, when you don't have geodesic convexity, you can say that there's a 1 on root k bound on the norms of the gradients at each of the outer iterate points. And when you have geodesic convexity, then the optimality gap is bounded by some constant times 1 on k, right? So those are the results we get from making that assumption, which is kind of what you expect. But now the more interesting, in my opinion, question is, when does the assumption hold, right? So the first thing I'll point out is that this assumption holds obviously when we're in Rn, right? And the subspace decomposition is fixed throughout. And we can do that because, as I said, in Rn, all the tangent spaces are identical to Rn. So we can just fix some subspace decomposition of Rn and use it throughout the algorithm, right? So that's fine. And then we can show that actually this assumption holds. So what that means is that tangent subspace descent is actually a strict generalization of coordinate descent in Rn, right? Another situation when this assumption holds is when M is a so-called product manifold. So it's equal to the Cartesian product of M different manifolds, so M1 to MM, right? Then if we have a point X in this product manifold, it can be decomposed in this way. So it's X1 to XM, superscripts. And the tangent space at the point X, right, you can write that as the direct sum of the tangent spaces of x1 for m1 all the way up to xm for m superscript m, right? And so when you have a product manifold, you can take the subspaces as in this manner, right? So if you're at the current iteration, you just look at the jth. If the current inner iteration is j, then you look at the jth component of the current point, ykj minus 1. And this should be the tangent space for mj, right? So that's another instance where the assumption holds. And on the general manifold, what we can do is fix. So at the start of the inner iteration, so if we're at some outer iteration xk, then what we can do is fix some orthogonal decomposition of the tangent space at xk. And then at step j of the iteration k, we're going to take this, the dj superscript k, and parallel transport it to the tangent space of the current inner iterate, ykj minus 1. So this is the choice of the subspace, and we can show that when we choose the subspaces in this way, the assumption will also hold. But I want to mention that the reason why we introduce the assumption is, I mean, we can analyze all of these without, explicitly defining the assumption. But the reason why we introduced the assumption from the previous slide is that computationally, if we were to implement this on a problem, it's actually quite expensive, or can be quite expensive, to compute a parallel transport operation at each inner iteration, right? So the assumption is designed to allow us to alleviate choosing this subspace selection rule, right? So there are more general rules that are possible. I want to illustrate this on an example of orthogonal matrices, right? So the manifold here is just the manifold of orthogonal, so square matrices, square n by n matrices that are also orthogonal. So the matrix Y is square and Y transpose Y is equal to the identity, right? And so the tangent space here is given by Y times A, where A is a skew symmetric matrix. So A is equal to its negative transpose, right? And the Riemannian metric is just, well, when you have two tangent vectors from Ty, Ya and Yb, it's just equal to the usual inner product of the matrix inner product for A and B, right? And the exponential map, if you want to move in the direction of Ya, starting from Y, then you just take Y and you multiply it by this matrix exponential. So this notation is the matrix exponential of A. Okay, and then the parallel transport on this manifold is the following. So suppose that we want to transport Ya, which is in the tangent space of Y, to the tangent space of another point Z, right? Where Z is given by the exponential map of Y times C, then the parallel transport formula is the following. You take Z, you multiply it by the matrix exponential of C on 2 transpose, and you multiply it by A, then you multiply it by another matrix exponential of C on 2. Right? So that's the parallel transport formula. But now let's talk about the subspace selection rule, right? So now suppose that we have some problem on the set of orthogonal matrices. We run an algorithm the tangent subspace descent algorithm, and we're at some outer iterate xk, right? Then we have to think about what is the tangent space of xk, and we can actually construct an orthonormal basis for the tangent space in this way, right? It just boils down to constructing an orthonormal basis for the skew symmetric matrices, the subspace of skew symmetric matrices. And so we can do that, and in this way, it's given by, this is the orthonormal basis, right? And so what we're actually going to do is order the indices. So these indices, there are, n times n minus 1 on 2 pairs of indices, IL here, that index the basis. So what we're going to do is, just order the indices in some order, right? I1, L1 to IM, LM, right? And then the subspace selection rule at the jth inner iterate, what it's going to do is just look at the one-dimensional subspace corresponding to the pair of indices IJ, LJ, yeah, right? But now, obviously, this is a one-dimensional subspace inside of the tangent space of the current iterate yk j minus 1 and not xk, right? So that's our subspace selection rule. So it's actually quite simple. All we have to do is just remember what order we chose for the indices, and then do this thing and project our gradient onto this subspace. Okay. So now we want to compare the subspaces that we select from our inner iterates, which is this collection here, to the orthogonal subspace for xk, the orthogonal decomposition for the tangent space of xk, which is this guy here. And so if we use parallel transport to bring it all back to the tangent space at xk, right? This vector here will become this guy, where ckj is just some matrix, so that you can some matrix that allows you to transport the current iterate back to xk, right? And so we want to relate these two objects, right? And so to prove the assumption essentially means that we want to show that when ckj is small, right, this set is actually close to this orthogonal decomposition below it, right? That's essentially the how we prove it. And this boils down to a continuity argument. So the point of all this is that it illustrates a non-trivial subspace selection rule beyond the three that I mentioned here. And it's more efficient to compute because we don't have to play with parallel transports, all right? We only have to deal with parallel transports when we analyze the algorithm, but not when we implement it. Okay, so I think I'm running short of time. So I had another section on randomized tangent subspace descent, but the ideas are very similar. We analyze the tangent subspace descent, we get some sufficient decrease, and we want to relate it to the sufficient decrease that we're used to, right? And we just need to make the assumption that it is. And we can construct a randomized scheme, a non-trivial randomized scheme for the Stiefel manifold. But I won't go through that in detail because I'm running short of time. And I'll also skip through the numerical results. And I'll conclude now to say that, the basic idea of this paper that I wrote with Huck is that we want to build an analogous algorithm to coordinate descent on Riemannian manifolds. And we do that and call a tangent subspace descent. We have counterexamples that kind of illustrate why this is a non-trivial task on a Riemannian manifold, and that really boils down to the problem of subspace selection. It's not straightforward to do that, because as you move along the manifold, the tangent space changes, and that complicates things. But we, came up with a condition that allows us to choose the subspaces in. Well, we came up with a condition for the subspace selection rule that allows us to have convergence, and we illustrated some subspace selection rules for the orthogonal manifold, and more generally a randomized subspace selection rule for the Stiefel manifold. If you're interested, the paper is on archive at this link, and we're happy to talk about any future work ideas that you may have. Okay, so I'll conclude there. Thank you all for your attention. Yeah, thank you again to the organizers for inviting me to give this seminar.
Thank you, Nam, for the nice talk. So maybe it's time for questions. I think we can have time for 1 or 2 quick questions. So if you have any questions, feel free to ask in here. Let's see any questions in here.
Yeah, I have a question.
Sure, man.
Yeah, thanks, Nam, for your nice talk. Some nice ideas in there. I have a question about curvature, because I don't think you really mentioned it. As far as I'm not an expert in this sort of area, but as far as I know, most of these results need some kind of like negative curvature in order to prove convergence fully. So you have like a Hadamard manifold. Is it the same for your work here, or does curvature not play any role?
Yeah, Huck and I discussed this, and I think negative curvature does come in implicitly, but actually, if you look at the results, we somehow managed to get away with it. But that may be because our analysis is kind of like a worst case analysis. Let me try and illustrate that in the slides. Okay, so for instance, right, these are, okay, I've hidden a lot of the constants here, but these are the convergence rates we get for our algorithm. And if we actually compare that to the convergence rates on the Euclidean setting, this factor of m would actually disappear, right? And I believe that the factor of m is there for the manifold setting because of curvature. Now, our analysis, I think, does not take into account the curvature, right? So we get a factor of m there. But I think if we do account for the curvature, and I don't know how to do this, but I think if we find a way to account for the curvature, then the factor of m will kind of be improved a little bit based on how curved the space is. So we didn't explicitly look at it, but I think that's where it would come in.
Okay, thanks.
Maybe that's hidden in the f is geodesically convex, because maybe it's otherwise, if you don't have this kind of curvature, maybe it's very difficult to find such an f.
Sorry, could you repeat that again?
If you assume that the function f is geodesically convex, then maybe this tells you something about the structure of the manifold in the first place.
Yeah, maybe. I thought, yeah, I'm not sure about that. I always thought of, I'd have to think more about that. I always thought of, the manifold and the function f is kind of separate, but maybe you're right. I'll have to think more about that.
And I have one question.
Yep.
Do you prove global convergence?
Yes, only for geodesically convex functions. I mean, for non-geodesically convex functions, we prove convergence to a stationary point. But I think your question is, do we have to start close enough to the optimal point? No, we don't. These rates are global. Yeah.
So the coordinate descent does not destroy this property, because I mean at the end all is governed by continuity of the metric, but at the beginning it's not so clear to me. I mean, when you start out and you're far away from the minimum, it's not so clear to me what coordinate descent will do, whether this can become too slow.
Well, whether it becomes slow or not, I think depends on, you know, your subspace selection rule. So as long as, you know, that's good, then we will get convergence.
Okay, thanks.
Yep.
Thank you. Maybe I have just a very quick question. So I think in manifold optimization, I think the exponential map is usually much more expensive than doing the retractions. Is there a way for you to incorporate the retraction techniques over there?
Yeah, we're actually thinking about that now. I think there is, but you know, the paper posted on arXiv does not do that. But we're fairly confident there is a way to do that.
Yeah, that's good, I think. Okay, that's my question then. Is there any further questions in here?
I had a quick one.
Yeah, sure, go ahead.
Yeah, so thanks. It's a nice talk. One thing with coordinate descent that people have looked at is essentially parallel updating, where you update each coordinate independently. Is there something that you've imagined that would be analogous in this situation, or does the manifold kind of make that way too hard to do?
Yeah, that's a good question. I've thought briefly about that before. Can we do parallel? I mean, I think there is. I think there is, but I think we would have to look at, you know, specific instances of manifolds. I don't know if they'll work generally or not for any manifold. They may work for specific instances of manifolds. So, for instance, maybe something can be done for this orthogonal problems on the orthogonal manifold that we can devise a scheme for. I'm not sure about generally, but I'm confident that something can be done for specific manifolds. Yeah.
Okay, thanks.
Yeah.
Okay, so in the interest of time, let me propose we can stop in here. Thank you very much for the nice talk, and also thank you for the discussion in here. So if you have further questions or comments, I invite you to contact NAM directly so that we can get together and talk about that. Okay, so maybe let's please join me to thank the speaker again. So I guess we will continue our next talk maybe in next week, I think. Right. So thanks very much for joining our webinar. So, and also thanks for NAM for the nice talk.